Good morning, everyone. My name is Syed Mohammad Zarif Tamid, and I will be presenting our paper, Comparative Analysis of Modern Machine Learning Classifiers for Pulmonary Disease Detection using Tabular Clinical Data. I will be presenting this paper along with my group mate Noor Hossain Takwar. As we all know that lung cancer is a very severe disease and it causes lots of deaths worldwide every year. And the uh, lung cancer is often diagnosed at a very late stage. So, early detection is a challenge in this field, and the methods that are used to detect lung cancer are very intrusive, as like X-rays and other physical diagnostic tools. Machine learning helps bridge this gap of late diagnosis by uh, using tabular clinical data like lifestyle choices as well as medical history, and uses them to predict whether the individual is at risk of having lung cancer or not. So our research also aims to do the same thing by using machine learning algorithms on tabular clinical data. We are going to predict whether a patient has or does not have lung cancer. A significant number of studies have already been done on this field, which is about predicting lung cancer with machine learning models. All of the studies achieved very good results, and they also uh, use the traditional machine learning algorithms such as XGBoost, random forest, and other to algorithm logistic regression, decision trees, SVM, etc. The main issue that the researchers faced was a missing data issues as well as a lack of standardized data sets that would help reproduce the results for the studies. Our study contributes to this field by using newer algorithms such as LightGBM and CatBoost, and helps to compare them with traditional models such as logistic regression, XGBoost, and random forest. Moving on to our methodology section, describing our dataset. Our dataset was taken from Kaggle. It had 5,000 entries and 18 attributes in total. The target column was pulmonary disease, which was a binary yes or no column, and this determined whether the patient had lung cancer or not. This huge number of dataset helped us to avoid overfitting issues. And moving on to the pre-processing stage, we initially cleaned the data. After importing the data, we checked for null values and duplicate rows, but we did not find any null values, nor did we find any duplicate entries. So after that, the target variable was converted into a binary 0 and 1 column. The target column, the pulmonary disease, was mapped into a 0, 1 column by using 0 for no and 1 for yes. The dataset was then split into features and labels. The target column was assigned one variable, and the entire dataset without the target column was assigned another variable. And then we used the standard scaler to normalize values like energy level, oxygen saturation. These were the continuous features, and we normalized them to avoid any imbalance issues. So after this, the dataset was split into a 70-20-10 ratio, where we used 70% for training, 20% for validation, and the rest for testing. This ensured that our model was fairly evaluated. That would be all from my side. My group mate Noor Hossain Takwar will continue the presentation.
Hello everyone, this is Muhammad Munsin Takwar, and I will be talking about the remaining parts of our research project, exploratory data analysis, learning phase, result discussions, and conclusion. Now we start with the idea analysis to better understand the distribution and relationships within the data, prepare it effectively for model training. Now we first visualize the distribution of the target variable using bar chart. This shows the reasonably balanced data set between healthy individuals and those diagnosed with pulmonary disease. Now we obviously know a balanced class distribution is very important because it helps prevent model bias toward the majority class and supports effectively learning from both positive and negative outcomes. Next, we used box plots to compare the distribution of numeric features uh, among two classes, patients with or without the pulmonary disease. These plots were especially useful in identifying which features differ significantly between the two groups. Now, then we constructed correlation treatment to visualize relationships among numeric features and identify any potential multicollinear. Now, this was crucial to avoid redundant features that could negatively impact model performance. Now, if we go to the learning phase, we can see that we selected six machine learning models which are distinct strengths. Now, few recent machine learning classifiers were implemented along with some traditional machine learning classifiers uh, to have a fair comparison. Now, logistic regression, as we know, is a supervised machine learning algorithm used for binary classification tasks. Now, we implemented LR as our baseline classifier due to its interpretability and suitability for binary classification class. Now, it was created as a minimum baseline model to compare with other complex models. It also helped run initial diagnostics in the dataset to avoid any implementation issues if we had any data issues or any issues to detect. Now, similarly, random forest and light GPM were implemented. Random forest for being the ensemble learning method that creates multiple decision trees, each tree being constructed from a random subset data and features. Now, obviously, this helps reduce overfitting by encouraging decision trees. Now, light GPM is a fast and highly efficient gradient boosting model that excels with tabular data, as we know. Then again, XGBoost was and CatBoost was implemented. XGBoost being a regularized boosting algorithm known for accuracy and robustness, and CatBoost designed specially for tabular data with built-in support for categorical features and a focus on preventing overfitting. And last but not least, NLP, a neural network capable of modeling complex non-linear relationship, was implemented. Now, we used 70-20-10 split for training and relational testing for uh, this model implementation. Now, if we go to the results and discussion part, we will see that the results of the 20% validation set uh, were compared. And if we talk about accuracy, then random forest, light GBM, and cat post were the highest performer in the sector with 0.916 as the accuracy. And with the classifier logistic regression, XGBoost were lower with accuracy of 0.91, 0.906, 0.904 respectively. Even though CatBoost Light GPM and Random Forest had identical accuracy, CatBoost slightly outperformed others in advanced code, which reflects its balance between precision recall vital for healthcare applications where both false negatives and false positives carry real-world consequences. Now, all the every model's confusion metrics with classic reports were generated and upper and bar chart were generated for accuracy, and another bar chart was generated for pulmonary disease plus F1 score. That helps us compare the models and choose cat boost as the best model as it has the highest F1 score and highest accuracy in all the other models. Now, CatBoost performance was further validated on the 10% test set, where it achieved accuracy of 91.2%, precision of 87.0%, and recall of 92.2%, F1 score of 89.5%. Now, the classification report showed F1 score of zero point 0.9 for disease positive trial cases and F1 score of 0.92 for disease negative cases. Now, these results indicate consistent performance across classes, not just during validation, but in completely unsafe data. Now, in conclusion, we can say that our study demonstrates that modern machine learning classifiers, particularly can effectively predict pulmonary disease from tabular clinical data. Now, while multiple models, including light GBM and random forest, delivered strong results, CatBoost emerged as the most balanced and consistent performer, both in terms of F1 score and recall, the latter of which was highest at 92.2% on the test set. Now, the high recall means that CatBoost can accurately identify the majority of patients with lung cancer, minimizing false negatives, something critical in every stage of cancer detection. So with a test, F1 score of 0.895 can use proofs. It can generalize well beyond training data, maintaining strong diagnostic performance in real-world scenarios. Now, from a healthcare perspective, this model could be deployed as a decision support tool in resource-limited environments, such as rural clinics or developing countries where access to imaging and lab diagnostics is restricted. Now, it could flag high-risk individuals based on routine health checkups and symptomatic data, providing early alerts to medical staff for further investigation. To summarize, Canvas not only leads in metrics but shows clear practical potential for real-world deployment in predictive healthcare. Thank you very much for your attention. This concludes our research project. Thank you.